Nahoy. Chemical bonding, lecture 6. We're going to switch from ionic compounds to covalent compounds. So while we did Lewis structures of ionic compounds with atoms, brackets, charges, and dots, we have a slightly different procedure for covalent molecules because there's no transfer of electrons in a covalent compound. They're actually being shared between the two elements. So we have to have a different way to show that on paper to represent the bond that is formed. Okay, so we are going to be doing some work on scratch paper every time we have to do a Lewis structure. So these are the rules I want you to write down, and then we're going to practice them. Okay, so there's no visual examples for the rules, so write them down. All right. First thing on scratch paper you've got to do is you got to count up all the available valence electrons for all the elements involved. Count all the valence electrons and see how many you got. Second, we're going to draw a frame. So atoms that are going to be singly bonded to each other. And the central atom is the atom that makes the most bonds. Because remember, if you're missing electrons out of your electron valence shell, you're going to fill it up with a chemical bond. So if you have 2 missing electrons, you're going to do 2 bonds, 3 bonds, 4 bonds, 1 bond, etc. The central atom is the one that makes the most because it has the most connections to make. Complete the outer atoms' octets by adding pairs of electrons around the outside atoms. And then we're going to count all the electrons that we use because we've got to reflect. Did I use all the available electrons? If you haven't, what you're going to do is you're going to take one of the lone pairs of electrons on the central atom. You're going to put lone pairs on the central atom to fill its octet. I can't read. But if you used them all, we're going to transfer a lone pair from outer atoms to make multiple bonds with central atoms. So if you run out of electrons, you got to make a double bond. It basically turns out to be, okay? You don't understand these rules because we have to put them into play in order to really get them to work. So watch a chemist, me, draw covalent Lewis structures. Your final answer needs to be redrawn with dashes as bonds and lone pairs to complete octets. Okay, so here is the deal. Starting with the single covalent bonds. These are the simple ones. And hydrogen, H2. So the first thing I'm going to do is look at a periodic table. I see I have 2 electrons to play with hydrogen. And I have to remember, hydrogen is the only element out there that prefers a stable duet. So what I'm going to do is I'm going to draw the 2 elements connected with a bond because that's my frame. And now I'm going to count all the electrons that I have used and compare back to what I have to do in the first place. So this is 2 electrons. So I used 2 and I had 2. I'm done. So there is your Lewis structure for the simplest molecule in existence, H2. We're going to get more complex, okay? Now if I go to this next one, HCl, I'm going to count my electrons in play. Hydrogen has 1 valence, chlorine has 7. So I have 8 electrons to play with. So I'm going to draw my frame. I'm going to connect the 2 elements that are involved with a single line, which represents 2 valence electrons. Now I'm going to put lone pairs of electrons around the chlorine element. Why? Because, again, hydrogen doesn't fill up to 8. It only fills up to 2. So I start with the other element. Never start with hydrogen when putting lone pairs in. I'm going to fill it up with lone pairs of valence electrons. Now I'm going to count how many I used. Remember, that bond is 2 electrons. So I count 2, 4, 6, 8 electrons used, and I had 8 electrons to work with. So I am all set. My final answer is H, single line Cl, and Cl has extra lone pairs of electrons on it. I used all the electrons I was allowed to play with. Octet is good, and duet is also good. NH3. Okay, well, N, I look on my periodic table, has 5 valence, and hydrogen has 1, but there's 3 hydrogens. So 1 times 2, 3, 5, and 3, 8 electrons to use. I have 8 electrons to use, and I have to start with my frame. So nitrogen had 5. It had 3 lone pairs of electrons. So it's going to make 3 bonds. So I'm going to put N in the middle because it forms the most chemical bonds. I'm going to connect an H to each side. And now I'm going to look. Okay, so each one of these single lines is 2 electrons. Each. 2 electrons. So I've used 6 electrons used so far, but I have to use 8 that I started with. So I put a lone pair of electrons on the only element that can really handle it in this scenario, nitrogen. And my final response, I'd erase all my scratch work out of the way, and I get my answer there. I'd erase all my scratch work out of the way, and get my answer there. I'd erase all my scratch work out of the way, and I got my answer there. So when you're done, you erase all your scratch work or redraw your molecule, and you're all set. So that was simple single covalent bonds. These electrons are being shared between the two atoms, which is why we draw a solid line in this scenario. Let's see some double covalent bonds. Okay. Well, oxygen, again, you look at your periodic table, you see that it's got 6 valence electrons, and there's 2 of them, so I have 12 electrons to use. I'm going to start my frame with oxygen, single connected to another oxygen, and then I'm going to fill up all my electron pairs. Remember, there's 2 electrons being shared right now in that single bond, so I'm going to fill up. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've used up all my electrons, and I still see that there's something not right here. That oxygen on the right-hand side in this case does not have a full octet. So the octet is not working. Uh-oh, that isn't right. So what do? We share a second set of electrons between the 2 elements. This pair right here, I can flip down into another double bond. And when I do that, it would look like this. Now there's 2 electrons on that bond, and there's 2 electrons here. So there's 4 electrons shared between these 2 atoms of oxygen. And now if I count my electrons, 2, 4, 8, 10, 12. I used up all 12 electrons this time. So remember, I go back and I redraw my answer with just the single pairs of electrons and the chemical bond that's involved. And that's our final answer for what O2 would look like. CO2. Well, count your starting valence electrons to play with. Carbon's got 4. Oxygen's got 6 times 2, 12, 13, 14, 16 electrons to use. So what do? Well, carbon looks like this normally. It means it can form 4 chemical bonds, which means that it's got to be my central atom. I'll connect it to oxygen on either side because carbon can form the most number of bonds. Oxygen, looking like this, can only form 2 max. Okay, so that's how I figured where to put carbon. All right, now erasing that, just boom, I have to start filling in electrons. I have to use 16 electrons total. And I've used 2, 4 so far. So I'm going to go 2, 4, 5, 6, 7, 8, 9, 10. Just for symmetry's sake, 11, 12, 13, 14, 15, 16. Oh, cool. I used 16 electrons, right? Great. Unfortunately, carbon only has 4 around it. It does not have a full octet. These oxygens are happy, but carbon doesn't have the octet. So we got to fix that. We got to fix that by taking a lone pair off the oxygen on the left and turning it into a double bond. And doing the same for the oxygen on the right. So when I redraw these as double bonds, I'll recount my electrons that have been used. And I'll see, well, this guy here is 2, 4, 6, 8 electrons. There's 8 electrons around carbon and 8 electrons around oxygen now. So my octets are good, which means that my final answer looks like that. That's how a molecule of carbon dioxide looks. C2H4. Well, Carbon, 4 electrons times 2, so I got 8 electrons to work with on carbon. And 4 times 1, 8, 12 electrons, so 4 electrons here. So I have 12 electrons to play with. Valence electrons to play with. Let me just draw that over so that I have scratch room here. Got 12 electrons to use. Well, I'm going to take my carbons and I'm going to put them in the middle. And let's see. I like symmetry, so I'm going to put hydrogen on both sides. If you had tried to put all your hydrogens on one of the carbons or the other, things would be more difficult for you. Now I got to count my electrons. Remember, one single line equals 2 electrons. So I have 2, 4, 6, 8, 10 electrons used so far, which means I'm going to just put 2 more on a carbon. And now I have 12 electrons used. Cool, yay, I'm done, right? Well, not quite, because I got to check my octets and duets. Hydrogen's happy because it has 2 electrons in the chemical bond that it's sharing with neighbors. This first carbon here is all set, 2, 4, 6, 8 electrons around that one, but this one, no good on that carbon. So what do we do? Well, we flip those 2 valence electrons down into a double bond, making a double bond between those 2 carbon atoms that now shows a molecule that has 2, 4, 6, 8, 10, 12 electrons used, 12 electrons to use, and we're good. So we go back, we erase our scratch work, or redraw our molecule, and we are done. This stuff is probably one of the harder things to do in chemistry this year, okay? And it all follows the octet rule. It all follows counting electrons in a single bond, a single line in these cases, being 2 electrons. Okay, we've got lots of practice for it to make sure we get it right. Triple covalent bonds, guess what? It's going to be very similar to the double covalents, except that you might have to move 2 lone pairs of electrons to do so. Well, with nitrogen, I got 5 electrons for each nitrogen times 2, so I got 10 electrons to play with, to use. So I'm going to draw N connected to another N as my frame. And that's used up 2 electrons so far. So I have 8 more electrons to place. Let's put them here. 1, 2, 3, 4, 5, 6, 7, 8. Why do I do it that way? Because I love me some symmetry. That's just how it be. Now I count up the electrons. I used all my 10 electrons. But if I count my octets, I only got 6 electrons. So the octet is not observed in either case. No octet. Boom. So what do? I take a pair of electrons that are sitting out by themselves, and I toss them in and make a double bond. When that happens, there we go. So this guy over here, 2, 4, 6, still 6 electrons. 2, 4, 6, 8. This guy's got 8. So that octet's complete, but this one is not. So we got to flip another set in. See if we can't share some more electrons between these 2 nitrogens to get somebody stable. So we're going to flip that pair in, make a triple bond. Triple bond. So now I count my octets. 2, 4, 6, 8. So because there's 6 electrons shared, both nitrogens get to count those 6. So now this guy's got 8 electrons, and the octet's complete. And so does this one. 8 electrons, octet complete. So there our final answer is looking like that. Nitrogen triply bonded to another nitrogen. HCN. Oh, you threw me 3 atoms to play with, mister. This isn't fair. Count up your valence electrons. 1 electron for hydrogen, 4 electrons for carbon, and 5 electrons for nitrogen. So 1, 4, and 5 is 10. 10 electrons total to play with. Well, I can look here. I can see that carbon is going to form 4 bonds. Nitrogen will form 3 bonds. And hydrogen will form 1 bond. So the element I need to pick for my central element in my frame is the carbon. So that's the central. So I'll start carbon in the middle. nitrogen on one side and hydrogen on the other. Now I have to start filling up the rest of these electrons because I've only used 1, 2, 3, 4, 2 electrons here and 2 electrons here. So I have to put in 6 more electrons somewhere. Now hydrogen ain't going to take none because its duet is filled. So I got to put 1, 2, 3, 4, 5, 6. Huh. Well, hydrogen's good with its duet, carbon's good with its octet, but nitrogen is nowhere near happy right now. It's only got 4 electrons around it. So we need to flip some bonds in. Let's do 2 at a time here. If I flip both these lone pairs of electrons in to a triple bond, I will have carbon triple connected to nitrogen. And if I count here, I got a duet, check, octet, check, and then nitrogen's got 3, 4, 6, that's got an octet too, check. So our final answer there, HC triple bonded to N. Last one. Thanks for hanging in there. I'm sure this lesson is going to keep people stalled out, so we'll do a lot of practice. 4 carbon atoms, 4 electrons, 2 times 2 carbons equals 8 electrons from carbon. 1 electron times 2 of them total equals 2 electrons from hydrogen. So I have 10 electrons to play with, to use. And we know carbon's going to be the backbone here. So we'll throw the hydrogens out symmetrically because symmetry is good. I've used up 6 electrons so far. I got to get to 10. So I'm going to put 2 here. And heck, I'll put 2 here. Me like symmetry. I like things that work. I count my octets and duets. My duet is okay here for hydrogen and duet okay here for hydrogen. But this one's only got 6 electrons around it. So its duet is not good. This carbon's only got 6 electrons on it. So its duet, or its octet is not complete. So what I do, I flip those extra pairs of electrons in to draw a triple bond between the 2 carbon atoms. Carbon's special because it can do that. It can do double and triple bonds to other carbon atoms. It makes a very complex possibilities of chemistry occurring. So there's your final answer for C2H2. And whew, I think we're done. We are. There's 1 page of practice on this because drawing Lewis structures is not huge. It's just important to me. That's why I want you to do it. So thanks for watching. Use your periodic table to do these pages and back it up with a Google Classroom assignment.